Welcome everyone to Mohamad Louai Shehab's PhD defense. Mohamad has been working with me for 5 years. I will admit something. I still have trouble spelling his middle name with too many vowels in there, but I am sure I learned it now. A few anecdotes about Mohamad. So he holds one of the records in the group that I wish none of my students will break. I think he had the most number of surgeries during his PhD. But he's healthy now, and he did a great thesis he will present. One other thing, it took him a while to decide on what he's going to work on. He tried different topics, and I think it motivated him that nothing is Markovian in the real world. So he's going to talk a lot about learning non-Markovian reward structures. With that, the stage is yours.
Thank you. So thank you, everyone, for being here for this big day. I'm excited to be talking today about some of the stuff that I've been working on for the past couple of years. The title of my presentation is Learning Structured Reward Representations for Reinforcement Learning. Now, before I start, a disclaimer for people who see a lot of robotic defenses. In this defense, you're not going to see a lot of flashy robotic demonstrations or robotic manipulators going left and right. My thesis is theoretical in nature. We have been interested in sort of tackling some of the theoretical aspects of multiple learning algorithms. So again, the motivation for my work is the outstanding successes out there for reinforcement learning. I'm sure many of us have seen some major success story for RL, ranging from robotic manipulation all the way to beating the world champion in Go and mastering online games. And this begs the question of what is the secret sauce behind these successes? And the answer is, well, there's a lot of things. In reinforcement learning, there's no single bullet or there's no silver bullet for why things work. It's generally a combination of things that lead to these successes. But perhaps one common known thing is that a good reward function is generally important to enable these behaviors. Now, the tricky thing is that the relationship between reward functions and behaviors isn't always straightforward. So in the following slides, I'm going to show you examples where even with a seemingly well-specified reward function, you might not get the behaviors that you desire. So let's consider a simple example where we want our robot to stack a red block on top of a blue block. Now, this makes sense in natural language, but for our robot to be able to perform this task, we need to give it some sort of a mathematical description of this objective. So one natural way to do this is we say the following. The robot gets a high reward if it aligns the bottom of the blue block with the top of the bottom of the red block with the top of the blue block. Now, seemingly, this solves the task, because if you align them, you put the red block on top of the blue block. Now, when you deploy this on your robot, you get this kind of behavior. What the robot does is it just flips the red block. I hope you can see. What the robot is doing is that it just flipped the red block so that actually its bottom is aligned with the top, but it's not solving the task. So what happened here is that the robot found a way to get a high reward without actually solving your task. Now, let's look at this again. Let's keep the human in the loop, and we'll consider another example. Now, I want my robot to pick up this ball, and I want it to place at this destination. And this destination is colored in red. We're keeping the human in the loop here. So we're not specifying a reward function, but instead, what the human is doing is that they're observing these behaviors. They see the robot's actions, and then they give a reward based on that if the robot picked up the ball and placed it in the correct destination. So we're keeping the human in the loop. That should resolve the problem from previously. However, the robot still finds a way around this. In earlier versions of this work, which is some of the earlier version of RLHF, what the robot started doing is it started tricking the human annotator. Basically, it placed the robotic arm between the camera frame and the ball so that it seems that the robot is actually picking the ball. The human sees this, it gives us a reward, but the robot isn't actually doing anything. So once again, the robot or the algorithm found a way to trick the human annotator. So this goes to say that this phenomena is a fairly well-studied phenomena, or it got coined a term which is reward gaming, or reward hacking in reinforcement learning. So basically, these reinforcement learning algorithms focus so much on optimizing this reward signal that it avoids leading to the intended behaviors that you want. Now, one way around this is we've just flipped the process. What if instead of manually specifying the reward function, we start from expert demonstrations? So I show the robot what it should do, which is these behaviors from expert, and then I learn a reward function that in turn induces these behaviors. This way, I created a reward function that is compatible with these behaviors that I want my robot to achieve. Now, by construction, if I optimize this reward function, then I get these behaviors. Because by construction, this reward function is learned in order to induce these behaviors. Now, this framework is called inverse reinforcement learning. And my thesis attempts to answer some of the open questions pertaining to IRL. So, generally, there are three sort of open questions that I contribute to. The first one is, what environments are suitable to perform IRL in? This question is critical because you cannot learn from demonstrations in every single environment. A very simple example is, imagine I show you a kid that is going downhill on a skateboard. And I ask you, is the kid going downhill because they lost control, or they're just being silly and they want to have fun? And the answer is you can't tell. Because just by observing these behaviors, you can't tell what happened. Because in this situation, the environment, i.e. the gravity, is forcing these behaviors on the kid. So this goes to say that there's a subtle but important point in IRL. And that is, not all environments are suitable to learn intentions from demonstrations. Because a lot of times, the environment might be forcing these actions on the agent, and the agent isn't actually portraying its true intentions or reward functions. And this is something that I go over in detail in Chapter 5, where I characterize what environments are suitable to perform IRL in. The second question, and perhaps the biggest part of my research, is how do we infuse temporal structure into IRL problems? Again, a very simple example is, imagine you have a robot in a 5-state grid world. And there are two key landmarks. There's a key landmark and there's a lock. And we want the robot to pick up the key in order to unlock the lock. Now, the reward function in this case is time dependent or history dependent. In essence, the robot gets a reward only if it unlocks the lock after it has visited the key state and picked up a key. So this history dependence on the reward function breaks the standard assumption in IRL that the reward function is Markovian. And you want? Okay. So this breaks the standard assumption of Markovianity. So how can we go about this? Now, we use a key insight that this robot is generally acting based on a finite state machine that is governing the high-level logic of its actions. In this case, the robot tries to go find a key, and then after it finds the key, it tries to go to the lock, unlock it, and then it solves the task. So this sort of high-level object is governing sort of the transitions of the robot. And our key insight in this work in Chapter 6 is we show how you can jointly learn this reward function, which is non-Markovian now, and this structure, which is given by a reward machine in our setting, directly from demonstrations. We extend this work, and we ask the question, what if we don't know the locations of the key and the lock a priori? And in this case, it might be because we don't have that information, or we don't want to specify it for the robot. And in Chapter 7, we provide a method that learns the reward function, the reward machine, and the location of these important landmarks directly from demonstrations. The final question of my PhD, of my thesis, is how do we systematically infuse priors into choosing into the IRL problem? One of the things you need to take away from this talk is that IRL in general is ill-posed. Meaning, if you observe a single expert policy, there's a set of rewards that induce this policy. And again, if you look back at Chapter 5, for the same observed behavior that you saw, many reward functions induce that behavior. So choosing a reward function, a proper reward function from this set is critical. Because we don't want only to choose a reward function that is compatible with expert demonstrations, but we also want to choose a reward function that transfers well. So it needs to capture essentially what the agent wants. So in Chapter 8, we explore methods of infusing rationality priors, which are some sort of inductive biases that we know about these agents, in order to choose a proper reward function from this huge set. So together, these questions make the bulk of my contributions. No one talks about their first 2 chapters, so I'm going to talk about the last 3 chapters of my thesis. The first chapter is learning reward machines from partially observed policies, and this is joint work with Dr. Antoine Espiel. So again, the goal is to learn useful memory structures, in this case reward machines, for multi-stage reinforcement learning directly from demonstrations. Why are we doing this? I'm not going to motivate the fact that a lot of tasks that we want are multi-stage in nature. think about any time you cook a meal, you generally follow a recipe which has a very defined steps in order to achieve your final goal. Beyond that, I think one interesting thing is there has been recently a surge in interest in encoding these memory structures explicitly into VLAs, VLMs, etc. Perhaps most notably is a work from our very own Professor Nima Fazali's lab and startups such as Physical Intelligence, where these memory structures are explicitly encoded into these large language models and state-of-the-art policies in order to enable these performances. So in this work, we attempt to learn these memory structures from demonstrations to make them easier to use and specify. So let's get a head started with what are reward machines, because I assume besides me and Professor Ozai, no one knows what a reward machine is. Okay, so let's start with the motivating example. In this case, we have a 4x4 grid world, and we have 16 states. Again, this is an MDP. I'm not going to go over some technicalities, but this is an MDP where each cell here is basically a state in your MDP. Now, I say that my robot has to patrol the rooms in the order A, B, C, D. Now, what does A, B, C, D mean? By A, I mean an atomic proposition. And this is a high-level property that is true in these rooms. For example, I color-coded the bottom 4 left rooms by green. And I'm saying that all of these rooms share the same atomic proposition, which is A. What's happening is there's the labeling function that takes in your state, which is A1, and it outputs this atomic proposition. Think of these atomic propositions as a high-level property true at your room. For example, it might be that these bottom 4 rooms share the same temperature. It might be that they have the same item, etc. So there is something common between these rooms. In more technical lingo, it might be an abstraction of your state space based on these high-level properties. Going back, the task is to patrol the rooms in this order A, B, C, D. Now, in order to solve this task, the agent needs some memory of what it has done in the past. Think about it. If you want to patrol in the order A, B, C, D, I need to know what I have patrolled earlier in order to know what to patrol next. A reward machine is basically this memory. Formally speaking, I was debating whether I want to show this, but I'm going to show it anyways. Formally speaking, a reward machine is the following 5-tuple. Think of a reward machine as a generalized directed graph. If you don't know what a directed graph is, that's fine. You start with a set of nodes, which is U. In this case, I'm just showing you nodes. UI is the starting node, meaning this machine always starts from the same starting node. Delta U is a transition function, and by delta U, we generalize directed graphs. In this case, edges are generalized so that they also capture atomic propositions. So in this case, each edge is associated with an atomic proposition. Here we're saying that if you're in U1 and you observe this atomic proposition A, you transition to U. And if you're in UI, you observe A, you transition to U1. And I don't show self-loops. So any atomic proposition that you don't see is basically a self-loop in the corresponding node. Delta R is a reward function. And basically, eventually what I'm going to show is that this agent is going to traverse this reward machine. And it gets rewards for traversing this reward machine. And these rewards are shown right to each atomic proposition in each transition. You can see that in this reward machine here, the only way for this robot or the agent following this reward machine to get a reward is if it goes from U3 to UI by observing atomic proposition D, and then it gets a reward of 1. Cool. So the core idea is that reward machines allow us to rewrite tasks in a way that is suitable for reinforcement learning algorithms to use. Basically, what's happening is that the reward machine is directly giving the reward function to the agent. In other words, it's giving the structural formal representation of these tasks into the agent, which sort of goes beyond what we started with, where we specified this reward function. Now we have a very structured way of specifying the task. And of course, not all tasks can be represented with reward machines, but that's beyond the scope of this talk. So to see a reward machine in action, again, our own robot, and we're going to move this robot in the grid world. So the robot starts, it's going to enter the grid world. I'm going to keep track of a few things. The first thing is what node it is currently in the reward machine. In this case, it's the initial node, which is deterministically specified to be UI. Some of the things we're going to keep track of are the MDP state, the prefix history, the action taken, and the reward given. Cool. Now the robot gets to the state A1. So basically, it was at UI. It observed the high-level proposition A. The reward machine transitions to U1. The current robot action is go right, and it got a reward of 0 from that transition. Now the robot goes right again. It goes to A2. It's still an A. From U1, A is a self loop, so nothing changes. The robot now goes to B, which has the atomic proposition. It goes to state B1, which has the atomic proposition B. The reward machine now transitions to U2. The robot goes up, up, and then to D. You can see that the robot basically patrolled the rooms in the order A, B, C, D, and it traversed the reward machine in a way that eventually it went from U3 to UI by observing D. It got a reward of 1. So in essence, an agent which is following path, and this is a simplification of what's happening. An agent that is following path which reached this rewarding transition in the reward machine basically solved the task. So that is one way for taking this task, which is patrol the rooms in this order, and then we specified it in terms of a reward machine, a structure that the agent is trying to follow. Now going back, the motivation of this work is to learn these reward machines, right? Now in this learning algorithm, we need to figure out what the input is. And to figure out the input, let's take a closer look on these things that we kept track of. Here we said that the robot reached this state D2. It had observed this history AA, BB, CD. It decided to take the action down. Now at a high level, what's happening is that there's a policy object or a function that takes in as an input the state and the history that the agent has observed. And this policy samples an action. In this case, the action it has sampled is go down. Again, because we're saying there's a sampling happening, it means that there's an underlying distribution of which this policy is sampling from. In this case, it's a distribution over actions, up, down, left, and right. And in this case, because the agent is trying to patrol in this order, its highest level, most probability density or probability mass is focused on the action go down. This object right here is called the prefix tree policy. And essentially what we do in this work is we are given this prefix tree policy, we want to learn the reward machine, which essentially means learn the transitions of the reward machine and learn the reward function. Formally, the problem statement is the following. We are given expert demonstrations, which are provided as a finite prefix tree policy. We want to learn a reward machine that induces the same infinite depth policy as the true underlying policy. So there are two parts to this question. The first one is whether this is even possible in the first place. Because generally, you cannot just constrain yourself to a finite restriction of the policy and then induce the same infinite horizon, because there's an infinite amount of information that you're losing. And the second question is whether that's possible would be, how do you even do that? Again, reward learning is generally a very well-studied field in robotics. More precisely, learning reward machines has also gained some traction in the past few years. Here's a very non-exhaustive list of the works out there, but it generally captures what have people done for learning reward machines. A big chunk of work generally assumes knowledge of the reward signal. And in that case, they transform the problem into versions of learning automata which are compatible with input-output traces. Since this is an IRL setting, we don't observe the reward. Other works that don't observe the reward are constrained to Markovian single-stage tasks, which is, again, we are interested in non-Markovian. Yeah. Yeah, you only observe the policy, the prefix tree policy.
But do you know the ABCD has been accomplished?
No. So the prefix tree policy, it only tells you stuff like this. You only observe what the agent has done at a certain state and a given prefix history. You don't know what the reward machine is. You don't know what the reward is. You only observe what the agent has done given states and histories of prefixes.
Yeah, so if I have an expert policy which never accomplished the sequence of ABCD,
Yeah.
then it's impossible to learn the reward.
So you basically learn what is given in the policy. So if the policy isn't solving a task, you wouldn't be able to solve So I'm saying that the expert policy is solving this task. So this is the information. Yeah. So the expert policy is the demonstration which knows to patrol the rooms in this order. And I'm trying to learn what are they trying to do, basically. Thanks for the clarification. Cool. So again, some other works for learning reward machines in a more of an imitation learning setting assume access to the true reward machine state or the finite state machine state during learning. And in our work, we learn these reward machines directly from demonstrations, which are given by these prefix tree policies without observing rewards or states. The algorithm that we use is fairly simple. You start by assuming that the reward machine is a blank slate. In essence, this means that any transition, let's say transition A, from U0, or the initial node, it can transition anywhere, which makes sense because we don't have any information. So in the learning algorithm, this is represented as Boolean variables. In essence, so each subscript for the Boolean variable can be read as follows. You start from the node, in this case node 0. You observe this atomic proposition A, and you want to know where does that atomic proposition lead? What is the end of that edge? In this case, from node 0, which is this setting, and atomic proposition A, you can go to one of 4 nodes, which are 0, 1, 2, 3. Now, each one of these is a Boolean variable, meaning it can be a true or false. Now, determinism means that only one of them is true. So basically, if A from node 0 takes me to node 0, it cannot take me anywhere else. And this is what we call determinism. Now, let's do some quick calculations. In this learning problem, by just counting the number of possible assignments of these Boolean variables, it turns out that the number of potential solutions is U to the UAP. Now, in a 4x4 grid world with 4 rooms, this is approximately 4.2 billion solutions. So we have a huge solution space for even a small problem. Now, as I said, structural constraints, such as determinism or other stuff that are found in my thesis, they help reduce the size of the search space. But can we do more? In essence, by can we do more is how can we use this policy? Because so far I haven't used this policy. How do we use this policy in order to reduce or even find a solution in this large solution space? Now, the key insight from our work is that the prefix tree policy can be used to find pairs of prefixes, which we call negative examples. Essentially, these are prefixes that are guaranteed to lead to different nodes on the reward machine. And basically, encoding these different paths that need to lead to different nodes turns out to be all that is needed to learn a consistent reward machine. I know that meant nothing, so let's see that in action. So let's consider the following branches of the prefix tree policy. I'm going to consider this branch, meaning that the agent ended up in state B1, and it has visited AB. What does that mean? It means that this is my agent. It started in, let's say, A2. It observed atomic proposition A, and then it went to B1. So the history it has seen is AB, and now it's in state B1. And now the question to you is, given that this robot is trying to patrol the rooms in the order ABCD, what do you think the robot is going to do from its current state? It's going to go up. Because the robot is trying to patrol, again, in the order ABCD. It has already seen AB, so its task is to go to C now. So here, the actions go up. Now, let's consider another scenario where the robot actually started in this state. So the robot started in this state B1, and it observed this high-level proposition B. And I ask you, what should the robot do from its current state? OK, I need to flip my perspective. So correct, it's left. Because the robot needs to patrol in the order ABCD in order to solve the task. So in this case, you can see that at the same state, B1, depending on the history that you use to reach that state, your policy changes. In essence, this means that the prefix tree policy has to have a difference when it's assigning basically policies to these different paths. In essence, what that means is that walks on the reward machine and the true underlying reward machine that use A, B, and B need to lead to different nodes. Because if these walks led to the same node, then they would lead to the same policy. And that contradicts the observations or the expert's prefix tree policy. So for example, if I have one of these solutions from this large solution space, which assigns the follows, let's say B takes me from U0 to U1, and then AB takes me from U0 to U1. That's a wrong assignment. So I can eliminate that solution from my solution set. And the theorem that we provide is that if given an upper bound of the number of nodes of the reward machine, if we encode all of these negative examples in the prefix tree policy up to a sufficient finite depth, which is given by number of states times Umax squared, then that is sufficient to recover a consistent reward machine. Now, we provide also extensions where we also study the case where instead of having the true prefix tree policy, we have sample estimates, in essence, access to demonstrations, and we show how we can probabilistically provide variants of our negative examples in order to do the learning. We also provide a robust max-set algorithm for dealing with these approximations. So we test this framework on a lot of examples. Going back to this patrol task, again, the agent is just observing the prefix tree policy, and within a finite depth of this prefix tree policy, we are able to learn this underlying reward machine up to renaming, which is the best you can do when learning a graph. Similarly, we add a hallway between the rooms to sort of increase this depth requirements. It turns out that the depth requirement actually increases, but we are still able to recover the ground truth reward machine up to renaming. We also test transferability, where we take this reward machine that we learn, and we learn a reward function on top of it, and then we transfer our learning into a new environment, where basically we shifted the positions of the rooms. So the agent can just copy what it has seen in the first environment. And we can see that basically our algorithm is able to recover almost perfectly the ground truth performance with a very gradual decay as we decrease this upper bound on number of nodes. Another example is a sequential tower block stacking. You have 3 blocks which are distinct, and you have 3 piles, and the robot needs to stack these blocks in a certain configuration in a certain order. Fundamentally, this is not different than the first example. The biggest difference is a larger state and action space. We also experiment with adding an absorbing state into this, which also tests the ability of our algorithm to be able to recover a minimal structure representing your policy. We take this up a notch, and we test this on a two-link robotic arm that is trying to achieve certain poses in a certain sequence. I don't know if this is visible to you. This is my bad. I should have fixed the image. But in this case, the robotic arm needs to reach configuration in a certain order, which are colored blue, red, and yellow. So it needs to go there, there, and there. In this case, it's a continuous state space and a discrete action space. We discretize the state space. It turns out to be in the order of 17 million. And in this case, we have finite sample estimates of the policy. We employ the robust MaxSat algorithm. And we were able to recover 4 solutions. Now, here, one thing I need to note is that the ground truth number of solutions is 2. So there's only 1 misclassification in the algorithm. Lastly, and perhaps the most difficult example is we experimented on real-world mice data set. Disclaimer, I didn't collect the data set. So they water-deprived the mouse, and then they put it in a labyrinth, and then they sort of observe the behaviors of the mice. I think the original idea of the experiment was to see like learning abilities of mice. Generally, the water-deprived mice, what they do is they start from the start node, they go to the water port, they drink, and then they wander around. And in essence, the state space is just states in this labyrinth, and the actions are, did the mouse go left, right, up, and down? So we just employ our learning reward machines on this data set as it is, and we're able to recover a structure that represents at a high level what the mice are trying to do. So in this case, it keeps looping in its current situation, current state, until it observes a water port, and then from there, the policy changes. So this ends chapter 6. So in this chapter, we propose a method for provably learning reward machines directly from demonstrations or partially observed policies with robust variance and finite sample extensions. Is there any Zoom questions? None. Cool. Okay, so everything was crystal clear. Cool, that ends chapter 6. Chapter 7 is basically an extension of chapter 6, and again, it's with none other than Dr. Antoine Espiel. This chapter title is Active Reward Machine Inference from Raw State Trajectories. So again, we look at this grid world example, which was we needed to do patrol. The biggest difference now is that the labeling function is unknown. And again, going back to my motivating example, we don't know the locations of these landmarks. So basically, for the agent, again, the labeling function or the grid world is, again, a blank slate. The biggest difference is that now we don't have access to a prefix tree policy because we don't observe the labels, in this case, the sigmas of these states. Instead, we have access to perhaps the most simple object in reinforcement learning, which is not simple, the very well-known object in reinforcement learning, which is the history policy. And in essence, it's a policy that conditions in your current state and your current state trajectory. So now you are given this history policy, and you want to learn the reward machine, you want to learn the reward function, and you want to learn the labeling function. So prior work in this domain has generally attacked this problem from generally two perspectives. The first one is assuming a sensor model. So in this case, the labels are not fully unknown. There is some sensor that gives you estimates of what is the current label. And you use a Bayesian framework to update your estimate of these labels. Other works use off-the-shelf representations, which are like large pre-trained models, as a direct replacement of the labeling function. And that is basically task irrelevant because these models aren't trained on your specific task. So in our work, we jointly learned the reward machine and the labeling function purely from this observed history policy. The algorithm is a slight modification of our chapter 6 algorithm. So previously, we assumed that the reward machine is a blank slate. Now, we also assume that the labeling function is a blank slate. In the learning algorithm, this is basically adding Boolean variables. So for each state now, there is a Boolean variable capturing what atomic proposition is true at that state. So let's say, in this case, I define these Boolean variables to be AP sub 0, 0. The first index denotes what state it is, and the second one is what is the atomic proposition true there. So for example, for atomic proposition 0, for state 0, I'm going to define number of atomic propositions, new variables, because I want to know which atomic proposition is true in that particular state. So this AP is a user-specified upper bound of the number of atomic propositions. Worst case, you can simply set number of APs to be the state space, because you cannot have more atomic propositions than states. So let's do some, again, back-of-the-envelope calculations with a 4x4 grid world with 4 atomic propositions. It turns out that the total number of solutions in this case is in the order 10 to the 15. And for some reference, there are roughly 10 to the 18 grains of sands on Earth. So again, for a very simple, small problem, there's a huge learning space. But luckily, the same implementation of negative examples, which need to be modified for this new setting, it still recovers a consistent reward machine and a consistent labeling function from demonstrations. And I think the intuition here is that it turns out that these negative examples are really efficient in pruning the search space. In many cases, one negative example might eliminate 1,000 solutions that you have. Now, a big question we ask also in this work is, can we scale these learning algorithms? First of all, to problems requiring deeper policies or even larger state spaces. Because as you have seen before, the sufficient depth grows with the number of states of your state space. And for any reasonable problem with a larger state space, exhausting the policy after that depth is infeasible. So we propose an active extension algorithm. I don't intend to go so much over the details. I should have removed those slides. But the idea is, suppose you solve your problem, which is the SAT problem, with a certain depth, a depth that you can solve on with your compute budget. Let's say that depth is depth L, which is much less than the sufficient depth L star, which again is number of states times Umax squared. We call this depth a burn-in depth. And we need to truncate the number of recovered solutions. So the high-level idea of this algorithm is you solve it with this depth L, you obtain a number of solutions. Now, if you solve with a small depth, you have a gazillion number of solutions. So you need to just maintain a budget of solutions. There are solutions that you need to forgo. So what you do is, after you obtain this set of solutions, you sample a solution at random. Let's say I sample this one. And then I sample a node from this solution, and then I sample loops to this node. After I sample these loops, I assess the quality of each one of these loops. So again, what I did is I sampled one of these reward machines, I sampled a node, I sampled loops to that node. I take one of these loops, and then I assess whether it's a loop or not in the remaining reward machines. So in this case, it turns out that this ABCDB, which is a loop in this reward machine, is a loop and not a loop in the corresponding reward machines. Now, we define this quality of this pair as the number of solutions for which this pair is a cycle or a loop. And in this case, it's 2 out of 5. So 2 out of my 5 solutions have ABCDB as a loop, and 3 of them don't have it. Now, the idea is we query the history policy with the pairs that have the highest loops. The high-level intuition is the following. If one of these loops splits your solution in half, meaning if it's a loop, half of them are consistent, half of them are not. If that loop is actually a negative example, when you ask the prefix to your policy, the ground truth policy, then by just one negative example, you eliminated half of the solutions in your solution set. So this is the sort of logic for this extension algorithm. It tries to find loops for which the current set that I have sort of have a largest mismatch on whether it's a loop or not. You go, you ask the prefix tree policy, is that a loop or not? If the prefix tree policy says, this is actually not a loop, these two cannot lead to the same node, then any reward machine that assigned them to the same node is a wrong reward machine and needs to be eliminated from the solution set. So we again experiment this algorithm on a variant of this grid world where the robot needs to pick up stuff from this state. It needs to drop off at a drop-off location, and it needs to avoid this area right here. So the reward machine is given by the following structure right here, where the agent needs to perpetually basically pick up and drop off, and avoid this state. Now, importantly, what's happening is the agent doesn't have access to this map right here. All you see from this agent is what the agent has done in different states and its different state trajectories. The learning algorithm doesn't have access to the reward machine, the reward function, or the labels. It just has an access to the states, raw states. And in our work, we show that we can learn this underlying reward machine and underlying reward labeling function, which is this gridding of the space, up to renaming within a certain depth for different experiments. And again, we experiment with our active extension algorithm, which is able to recover this ground truth within a depth 12 of the policy. Whereas if you just randomly query the prefix tree policy, you basically don't have any learning, which is represented by the flat line on the top. Going back to my favorite example, the patrolling cat. Again, we have a robot that is patrolling the rooms in this order. It doesn't know what room is A, what room is B. It only observes states. Again, we're able to recover up to renaming, the reward machine, and the underlying room structure. And this is room structure independent. Even if I plug in a Tetris room structure that the agent is trying to follow, the algorithm is still able to pick up on these labeling functions, basically. Again, the active extension algorithm works pretty well in this setting, whereas a random method that tries to query this prefix tree policy doesn't perform quite as well. The right figure actually shows this branching complexity, showing that any depth of the policy beyond depth 10 is practically infeasible on at least my laptop. Whereas this active extension algorithm that maintains a fixed increase, basically a linear budget increase in the number of prefixes, it performs pretty well even for larger depths. Again, there are a lot of memory gains that could be done with this active extension algorithm, as well as computational gains in terms of reducing the computational requirements for solving the SAT problem, and also reducing the memory requirements. In this case, we go from 25 gigabytes for the exhaustive storing of the policy, all the way to 0.1 gigabytes. So in summary, this chapter extended our reward machine learning framework to the setting where even the labeling function is unknown. And we provided also an active extension algorithm that is aimed at reducing the memory and computational requirements for exhausting the policy. Now that brings me to the last chapter, which is infusing priors. Gratefully, this chapter won the Outstanding Student Paper Award at CDC and joined with Alperen right here, who came just in time. So again, the motivation here is that inverse reinforcement learning is ill-posed. And I've already hinted at this previously. It is the fact that many reward functions fit the same behavior. And this is assuming a static reward function now. So the reward function doesn't change with time. Pictorially, what's happening is you imagine that there's a policy in this policy space. I denoted by this pi star. Now, this policy corresponds to a set of rewards that perfectly explain this policy. So let's see an example of what's happening here. Let's consider, again, a mouse in a grid world where you just have a very simple home and water port. The available actions to the mouse are go left, right, and stay in your current position. Now, let's say that the mouse, from its current state, it decides to go right. So the demonstration that you see from the mouse is it went right. And I ask you, does the mouse want to go to the water because it likes water or it's thirsty, or it's just trying to avoid home. And the answer is both hypotheses are equally likely. What this means is that these hypotheses, liking water and avoiding home, are basically points in this reward space. And here I'm denoting by the red point, the reward function that likes water, and by the orange one is the reward function that dislikes home. Now let's assume that the mouse actually, the true reward function of the mouse is that it wants to go to the water. To see why having a large reward set is problematic, we're going to look at a new environment. So I just shifted the positions of the home and water. Generally, what you do in IRL is you have your observation, you learn this reward function. In this case, we learn the reward set. From there, you need to specify at least a reward function for which you're going to optimize for behaviors. Let's say we chose that the mouse actually has this reward, which is it wants to go to the water cell. We optimize for a behavior in this environment, and the mouse actually does the right thing because it has a high reward for the water, and it goes to the water cell. Now, if we instead assumed that the reward function is the mouse doesn't like to be at home, which is perfectly consistent with the observation in the first environment, and we optimize for a behavior in this new environment, then the mouse is going to stay in its place because it's trying to avoid home. And clearly, this is not what the mouse wants. So the takeaway message so far is choosing a good reward function from the set is critical, and especially when we're transferring to new environments. Yeah.
Another view of that is not the reward function is not well defined, is your state is not well defined. Because the reward is mapping state to a number, right? So here the state is where the mouse is, but not including where the home is and where the water is, right?
Yeah, perfect.
Yeah. So can you comment on that?
Yeah, so you just like hit the nail in the coffin, as they say. So basically, that's the idea. It's that we are depriving the mouse from important information, which is these featured landmarks that we have. And essentially, our work is how do we systematically infuse this information into the state space definition.
Okay.
So that is exactly what we do. Cool. So choosing a good reward function from this set is critical, especially when we want to transfer to new environments. Now, the setting of this chapter is the reward function is time varying. One example for this is how do reward functions are generally time varying is imagine you have a PhD student that is trying to choose a conference to publish their papers. On the x-axis, we have time, which is the time of their studies. And on the y-axis, we have the reward weights. We're going to keep track of two reward weights. The first one is the conference quality, and the second is the conference location. And generally, your preferences change over time. So this is a very real-world example of how your reward function changes over time. So in this setting, it's pretty clear that even more reward functions fit the same behavior because you have the same ambiguity, you concatenate it over time. So you have even a larger set consistent with the same behavior. Pictorially, you just concatenate it over time. Now, this problem is very hard to solve without any priors. Now, two things I need to talk about here are what do I mean by solve and priors. Solve means choosing a reward function from this set that truly captures the agent's objectives and transfers well across environments. And prior means these rationality priors that we infuse into this problem. Basically, how can we give this agent structure of the problem to help us choose a reward function that transfers better? In this case, we're going to deal with two priors. The first one is that real agents generally change their objectives sparsely. Think about anytime you are driving, you don't just all of a sudden change your objective to go back home or go to the work or go to the supermarket. Generally, your reward function is well behaved across time. And the second prior is that these objectives are generally functions of a few features, and more about that later. So the central question of this chapter is how can we systematically infuse these priors into choosing a good reward function in the time-varying reward setting. Setup and background, this is something that I've hid from you all throughout this presentation, but the setting that we're using here is a Markov decision process. In this case, it's tabular. We have finite state and action spaces, and we have a finite horizon. The objective function is max entropy reinforcement learning, which is a finite discounted reward with an entropy regularization. We are given access to an expert policy, which is some maximizer of this function for a certain reward. Now, the inverse reinforcement learning problem may be sort of more in a functional manner. It's given by the following function. You can think of IRL as a function that takes in as an input the expert policy, and it outputs this set of rewards that are consistent with this policy. And again, pictorially, IRL of a policy is this set right here. Now, the first question before we start working with this is, do we know in closed form what is the set of rewards that induce a certain policy? And the answer is yes, and this is due to chapter 5, where we show that this reward consistent with a policy is given by an affine set. Without going over details of this set, what matters most is this set is defined over variables, which are your time-varying rewards. So you take your reward over each time step, and you concatenate them. Another important object is the time-varying value function. You need to also concatenate that. You construct a matrix, which is based on the MDP dynamics. Now, what matters most is that this matrix is a wide matrix, meaning we have a large feasible set, and yet again confirming our intuition that for a single policy, there's a large number of rewards inducing that policy. Cool. So to reiterate, how can we systematically infuse these priors into choosing a good reward function from this set? Recall our priors, there are two priors. The first prior, real agents change their objectives sparsely. And the second one is that these objectives are functions of a few features. The key idea in this work is that we turn these priors into nice loss functions. By nice, we mean two things. The first thing is that these functions are easy to optimize. Alperen, you shouldn't be there. The first thing is that these functions are easy to optimize. And the second thing is that they should serve as a good mathematical surrogate of our priors. Eventually, we end up solving problems of this form where we minimize this loss function subject to feasibility constraints. Now, let's look at our first prior. Real agents change their objectives sparsely. And again, we said we want to specify this loss function, which captures this mathematically. One way to do this is the following. We say that among all the feasible rewards, we want to find the reward function with a minimum number of switches. In essence, I want RT to be equal to RT plus 1 for as many time steps as possible. If we define delta RT as a change in the reward function between two time steps, and we just define the zero norm of this vector valued sequence, which is basically the number of time steps for which the norm is non-zero. In essence, it means the number of time instances where there's a switch in your reward function. So if we want to maximize sparsity, meaning we want to find a reward function with a minimum number of switches, we can minimize this zero norm of this vector valued sequence. And that should give us the minimum number of switches. Now, the problem here is that minimizing zero norm is a non-convex and hard to solve problem. There are multiple ways to deal with this. The first one is you just do a L1 norm relaxation. And in that case, you need some assumptions on the structure of your problem to say that the solutions are equally optimal. The second option is you can exploit the extra structure in your problem to find an efficient algorithm, and this is what we do in this work. What we do is basically we provide a greedy algorithm for finding these switch times, and it turns out that that greedy algorithm is optimal due to the structure of the problem, basically due to the affine space structure that we have. Greedy is optimal in this setting. So at a high level, what's happening is you keep growing intervals where you say, oh, I can assume a constant reward up until this interval. And then at some point, you hit an infeasibility point. And you detect that as a switch time. And you keep doing this until you find all of your switch times. So our first contribution is that our greedy algorithm solved this IRL problem with max sparsity exactly with polynomial time. The second prior, which goes back to Professor Ying's point, is that these objectives are functions of a few features. Feature-based rewards means that the reward function can be written as follows. There is RT, which is the reward at time step t. It's given by a matrix U times these time-varying weights alpha t. U is this feature matrix, which is this low-rank structure that is governing your reward function. And alpha t is the time-varying weights. So I'm assuming that the rewards over the time steps, they share the same U, because U doesn't have a subscript t, but the alphas change. Now, most importantly, if you optimize over both U and alpha, because both of them are unknown, we only know that there's a decomposition of the reward in this form, but we don't know U or alpha. So if you optimize over both, we have a bilinear program. Plus, we have to choose K, which is the feature dimension, which is how many features do I have. Our way around this is instead we just concatenate our rewards to construct the following matrix. You just concatenate time-varying rewards. The observation is if we minimize the rank of this matrix, we obtain the minimum number of features. Because basically now you have a column span of your rewards that is capturing the important features for your reward function. Again, minimizing rank is a non-convex and hard problem. However, it admits a very good convex relaxation. And this is due to seminal work by Ben Recht et al., which showed that a very good surrogate for minimizing rank is actually minimizing the nuclear norm of a matrix, which is given by the singular values of the matrix. So we solve that. That's our loss function, minimizing the nuclear norm. After obtaining a solution, we obtain our feature matrix U by basically finding a column, by finding a basis for our column span. And then our time-varying weights are basically the weight evaluations or the weight representation of our vectors in our basis. Second contribution is that we also deal with policy estimates instead of the true policy, basically by probabilistically inflating the feasible reward set. For experiments, again, we assume we have a grid world where we have a home port and a water port. We assume a horizon of 50, and we randomly sample switch times to solve the forward problem. So in essence, what we're doing is we are specifying a reward function that is fixed along these intervals, and then we randomly switch the reward function. We solve the forward problem, and essentially we show that our greedy algorithm is able to exactly recover these switch times, and with more and more samples, our finite sample extension is also able to match the performance of the true policy, albeit with a large number of samples. Again, to test transferability, we designed variants of our grid world where we add blockings and sticky states to sort of alter the dynamics of the MDP, and again, to test transferability. And in this case, going back to Professor Ying's point, we know that the two important landmarks that matter for the reward function are the home port and the water port. So we know that there are landmarks that matter for this reward. And the idea is, can we learn these landmarks directly from the policy? And can we infuse a learning problem for which we are learning these landmarks? And this is what we mean by learning the feature representation. So in this case, we have a setting where the reward function for the water, or the reward weight for water, goes down with time because the agent starts thirsty, drinks, and then it's not thirsty anymore. And then the reward weight for going to the home state increases with time. So you can see that there's a sparse representation of the reward function where the only states that matter are the home state and the water state. By infusing this low rank structure, we are able to recover a qualitatively good representation of the ground truth rewards, as well as a very crisp representation of the feature function, which is capturing the positions of these landmarks. We also test transferability, to which this policy learned from this prior infused reward is also better at transferring. So this brings me to the end of my presentation, and now for the hardest part. Acknowledgement. So big thing is that I didn't practice the acknowledgements, so it's a rookie mistake, but we'll see how it goes. Of course, the biggest thank you go to my advisor, Professor Nejmi Ozai. Do we have another 40 minutes for me to go over acknowledgements? So again, I think one common theme that we have seen from Dr. Karagulle and Dr. Zhang is the fact that many of us came to your lab with not a lot of skills in doing research, but you were kind enough to take us into your lab and sort of train us from the ground up to wherever we are right now. I'll be forever proud that I'm your student, and I'm super proud that every single paper that I have has so much of your contributions and flavors. One interesting thing is, back in 2021, I sent an email to Professor Ozai, and it goes as follows. Dear Professor Ozai, I hope you're doing great and staying safe in these hard times. And this is back in COVID. I will quickly introduce myself because you might be asking yourself, who is this? I'm a senior student in AUB, blah, blah, blah. I've chosen you to be my top choice advisor and would love to initiate some form of connection with you. I hope that I've maintained your interest to continue reading so far. this is the first milestone of my email. Proceeding on, I just mentioned a couple of things that I searched about Professor Oze and really captured my attention. Now, this is how I ended my email. And if you ask why ChatGPT is so poetic, it's because it's trained on such data. So at the end, I said, I believe that research is a difficult career, but also a wonderful one. The satisfaction that one gets of discovery and influencing other people's thinking is addictive. It has a lot of ups and downs and lots of stagnation points. It might lead to isolation. However, isolation is one of the shortest points to depression. And one of the shortest counters is to be united by a collaborative mission and a group dynamic which values working together towards common goals. By being such a good influencer, and of origins which share lots of common culture with my country, having you as an advisor and being part of your diverse team is exactly what I dream of for the next big chapter of my life. I hope I could hear from you soon. That will be the last and most important milestone of my email. And I indeed heard from Professor. I got rejected first, and then I got here. All the thanks also go to my committee members. I'm very fortunate to have a world-class committee that I will be forever proud of. Professor Abate, thank you so much. I don't know how many students out there can say that they swam laps with their committee member. Professor Panago, unfortunately, I don't have a lot of personal stories with you, but I've always had so much admiration and respect for you, so thank you so much for being on my committee. Professor Ying, my introduction to reinforcement learning has been in your class, and you were graceful enough to always answer my questions and give me a lot of feedback and motivate me to do research. Finally, Professor Vasudevan, even though he's not here, he's been kind enough to let me present to him asynchronously so that we can either celebrate or cry after this meeting. I'm so sorry, Dan, I didn't put your name. Robotics staff, I guess the first and biggest thank you goes to Denise. I don't know if Denise is on Zoom. She sent me an email. Again, Denise, the shining star of the robotics department. You have been a cornerstone for me in the department and a very important support system. So thank you so much. Damon, my first introduction to Tesla acceleration has been with you. So thank you so much for all the chats that we had and support. Samantha, Dan, and Kyle, again, thank you for always being there for anything that I need and for all the support. My main co-author, Dr. Antoine Espiel, again, I hope Antoine is on Zoom. Antoine has had so much effect on me. He helped me so much throughout various stages of my PhD, and it has been crucial for my growth also working with Antoine. And I think if there's an award for the best postdoc hire, it should go to Professor Oze for hiring Antoine. Again, biggest thank you to my research group. It's been a fun ride sharing all of this with you. I noticed that we don't have a lot of pictures with Alperen in them, but then I found this. So there you go. Again, my friends in Ann Arbor, you made this place feel like home. This is a picture of Gil smiling right there. So thank you so much for being, making Ann Arbor such a great place. I hope you all see yourselves here. Again, my friends in Lebanon, apparently as my friend group in the US grew, my friends in Lebanon shrunk. But again, I maintain a very set of close friends that make it worthwhile. My friend Mohamad, he recently became a dad, actually a couple of years ago, maybe a year ago. I haven't seen his son yet, but hopefully soon. Of course, my family. Biggest thank you go to my family. Unfortunately, I'm not of those lucky ones whose family could attend their defense. But my family has been irreplaceable for my entire journey. And thank you so much. And my brother, the star of the family, the first doctor in our family, and hopefully I'll be the second. Yeah, exactly. And finally, last but not least, Mariah, I don't intend to keep this long because I don't want to get emotional. But even though you haven't been there for most of my PhD, you've made the last part really worthwhile. So thank you so much for everything that you do. And thank you so much for being always there for me when I need you. And I love you. And most of the pictures are hand pictures because she doesn't like to be taken pictures of. And that brings me to the end of this talk, and thank you so much for listening.